add, right? So the moisture content went from 2.2 to 10.9 because now we added the water that was produced by the combustion. It's just the chemical reaction. And with that new water content, then we get our new air. And just in the chart, although we don't see it because it's outside over there, but so now the moisture content went down here from where it was 2 point something to where it ended up now is 10 point something. But it's over there, away from the computer, so we don't see it, kind of over there. So it's, the moisture content is 10 and the temperature is 210 now. Now, something else that we calculate there is the enthalpy of that air, and it turns out to be 246, here's the number, 246.4, that's the enthalpy. And then this tricky method here is to calculate the wet bulb temperature. So this is the guess of the temperature, and then what I did is I took a slightly different temperature, and I calculated using this. This is the vapor pressure, the moisture content from the vapor pressure, the enthalpy of the air, and I tried. So this is just a guess. You take this guess, and then you calculate the vapor pressure, the moisture content, the enthalpies, and you get an enthalpy that is not the same. There is an error, you see? It's not the same enthalpy. And then I take another enthalpy that is the previous one multiplied by a tiny number, just a little bit different. And then I calculate it again and I get another error. And then what I do is I find the slope of the errors and I say, if I want an error of 0, what would be the change in enthalpy, in temperature that I wanted? This was a method invented by Sir Isaac Newton to find the root of a function. Remember the root of a function? You want to find when the difference between your function and 0 is 0. So I say if my error here is 352 and my error here is 323, I want to find what's the value of x here that makes my error equal to 0. So I calculate that new number, and it's this one. And then I repeat the thing again, and finally I get here, and my error again is 0. And here is a plot of that. So it's just the Newton. It's called the Newton method to find the 0 of a function. You guys have used it a million times, I'm sure. Here is just 2 iterations, and you're done because it's almost linear. So it's the case of having the enthalpy and wanting to find the more precise wet bulb temperature. So this one is not far, but you see 47.55 ends up being 47.84. So we know the wet bulb temperature now, and you could compare that with whatever you measure. So with all that information, now we have characterized our combustion gas. And now what is important there is that we know that enthalpy. So we know more or less that case I was showing you. You know the enthalpy, so you know where it's going to go, approximately, right? Through which line it's going to move when you're going to do the drying. And then you can go and figure out, do an energy balance. So I did an energy balance there, and those are all the energy balance terms. And then that energy balance ends up producing a quadratic equation. So I put all the terms together into these three guys here, A, B, and C of the quadratic equation. And then I solved the quadratic equation. I included some heat losses from the work some of you guys did, and I ended up solving this quadratic equation. Remember the quadratic equation? Minus b plus or minus b squared minus 4 times a divided by c over 2a. But that's just the solution of the enthalpy balance of the spray dryer. The enthalpy balance of the spray dryer is the enthalpy of the feed plus the enthalpy of the air going in has to be equal to the enthalpy of the product going out plus the enthalpy of the air going out. That's it. What is the unknown there? The temperature of the air going out. We don't know what temperature that air is going to go out. We know what air went in, we know the feed went in at a certain temperature, but we're going to have to guess one temperature. That's the temperature of the product going out. Now, luckily, the product is a small thing, so we can afford to be wrong in that one and then correct it in the second iteration. Okay? So we get a temperature of 91 for the air, right? So what we are doing here is trying to replicate what we hope the spray dryer did in the experiment. Then we can check with the experiment. Did it do this in reality? Yes, no. So we can get a sense whether our model is more or less representing the spray dryer properly or not. Are we predicting that the behavior of that spray dryer properly? Maybe these 1200 losses are not so realistic. No? We can play with that, right? So those numbers in red are numbers that are sort of hard numbers, but in the sense that are inside of the simulation. They are not to play with them. They are supposed to be kind of intrinsic of the system. And there are other things here. For example, the fan is supposed to be moving always a fixed amount of volume of 237.2 meters cubes per hour that corresponds to a velocity of 1600 FPM in the tube. Maybe it's 1700, maybe it's 1750. We could never really get any fixed thing, no? Although the proponents of 1500, the 1500ians are certainly very much respected, so they can put 1500 if they want. They measured it many times and probably it's 1500. I put a little bit more because it seemed to fit better, but it could be 1500. It's just that there's a small correction for hot temperature. At higher temperatures sometimes it's a bit anyway. So it's a constant volume, and here is the calculation of the density of the air, which is the pressure, atmospheric pressure multiplied by the molecular weight of the air divided by the universal gas constant multiplied by the temperature in Kelvin. Fairly well-known expression. And then the mass flow rates is the volumetric fan, flow rate of the fan multiplied by the density, so that's the mass flow rate of the exhaust air. And then the other calculations have to do with, if you take that and remove the water, then you get the dry air, right? And that's one of the important things that we need to get. No? So the volumetric flow rate of dry air is very important for us. No? This mass flow rate of dry air after combustion, right? We call it dry air. So that's very important because things are really referred to that number. Right? Then everything gets multiplied by that number. Then mass flow rate of water that was going in, how much propane we used, how much air from the room, the moisture content. This is very important, the moisture content of the thing going out, because that's the one that uses the final point. This number goes up there, is linked here to this spot here, and then it defines that point, the final point of the drying. And then when I invented some number from the presentation of the other day also for the losses here here are the losses in the silver pipe that go up to the cyclone and in the second cyclone. So that cools down a little bit the air. It makes its enthalpy go a little bit low, and then the air cools down a little. And that gets represented by this little cool. But there is no water loss there because the air has already dried up as much as it could dry the particles, so it doesn't lose or gain water. So it just stay there. So we should be having these kind of readings in our wet and dry bulb thermometer at the end. This should be the reading that we get in the dry bulb at the exit of the bottom of the spray dryer. So what we can do is tweak some of the things so that our little model more or less follows the experimental data that we have. And then we can use that to make decisions or recommendations. So this is the idea. And everyone can tailor it to his or her own liking. So when you submit it in the exam, it has your own, it has to have your own flavor, or taste, or smell, or color. And have your own personality.
Most importantly, explain what you're doing.
Yeah, this is the most important thing. So make sure you put notes and things, note number one, and explain. Why is it doing this? Why am I doing this? Why is it? So you're going to explain. We want you to explain, right? So because using these tools that I took hours and hours to create, yeah, it's cool and all that, but that's not the idea. The idea is that you explain. Right? That you tell us that you understand why it's doing this way, and why this is done this way. And you can follow the calculations, and there might be things that you understand, things that you don't. Most of the equations, I put names to all the variables, so it's easier to follow what they're doing. And another thing, I left the A column also empty all the time, so that you can also use it always to put things like something like this, like a note there or something, right? You can always do that. And that's meant to be a study guide for you as well as a sort of your own little spray dryer to play with at home. Change it and tweak it, make it be similar to your own spray dryer or to whatever. So I think that's pretty much what I have to do with spray drying. So tomorrow, if you have more questions, you can. Of course, you can always ask me and whatever, no? And then we'll do something not quite the same, but with some similarity and some difference for distillation. Oh, we are so tired. Yes.
Are we going to be meeting at 1 o'clock tomorrow, or has that time changed?
No, today I'm very sorry, but they were trying to figure this out. Do you guys know the whole department has been restructured and they've been trying to get everybody together, and they only could do it today at noon, and I knew that meeting was not going to finish at 1. So
So tonight, if you want to go through